Okay, looks like we're recording the screen, getting audio. And let's take a look here. So we left off on this problem right here. We were talking about the inverse sine function and how we plug in a ratio and we get out an angle. And we ended up with pi/4 for the answer on this particular problem. So let's take a look at this next one where we've got cosine inverse of 1/2. So this is a ratio. I like to think of everything in terms of the unit circle. So if this is the x coordinate on the unit circle, we've got something like this. This is a 1/2. Hypotenuse would be 1, or the radius would be 1. That makes this other side here radical 3/2. We'd recognize this triangle right here as a special right triangle. This is the largest of the two legs. That means this is the largest of the two acute angles. So that's 60 degrees, or if we did it again in radians, pi/3. So there's our answer for that one. And now we're going to look at some things that are just a little bit more complicated than just solving those. And I asked you to think about why there would just be one answer to each of these. And we're going to discuss why there's just one answer to each of those right now. So let's take a look at this problem right here. It says graph y equals the sine of x. And graph its inverse, y equals sine inverse of x. And sometimes we also call that the arc sine. You'll see that occasionally. But if I were to graph the sine function, remember, starts at 0, goes up to 1, comes back down, goes down to -1, and then back to 0, and then just repeats that pattern. So it looks something like this. Now, you can see immediately that we've got an issue with this one, because if we're talking about inverses, the original function has to pass the horizontal line test, which this doesn't. So what we need to do is we need to restrict the domain, and we want to do it in as smart a way as possible. So what we do is we keep the domain close to the origin, okay, close to this, and we want to make sure that we cover all the ratios that come out of the sine function, all the way from -1 to +1. And the easiest way to do that is to just restrict the domain from -pi/2 to pi/2. Now, I'm going to redraw this. You'll notice that this scale on this axis is a little bit large. That's a little bit larger. That's because this does represent 1, and this represents -1, and this represents pi/2, and this represents -pi/2. So if I were to draw this really accurately, it would look something like this. We've got this point right here, definitely goes through 0, 0, and then -pi/2, comma, -1. So it looks something like this. That's what the sine curve would look like. Now, I'm going to label a couple of points. This point would be pi/2, comma, 1. This would be -pi/2, comma, -1. And then if we were to graph the inverse, remember, to find the inverse, all we have to do is reflect it across the line y equals x, or switch every x for y. So instead of graphing pi/2, comma, 1, I'm going to graph 1, which would be about right here, because pi/2 is about 3.3 divided by 2, about 1.5. So we're going to be about right here and about right there, and pi/2. So we're going to switch this, 1 and pi/2. So pi/2 would be up about right here. So this is going to be 1, comma, pi/2. 0, 0 wouldn't change because flopping those around doesn't make any difference. And then this is going to be -1, which would be about right here, pi/2. So that's going to be about -1.5. So it's going to look something like this. So this is what sine inverse looks like. So this is y equals the sine inverse of x, and that original one was y equals the sine of x. And you can tell just at a glance by tilting your head just a little bit, they are indeed reflections across the line y equals x. So there we go. Now, so you'll notice if we're just talking about the sine inverse, you'll notice that the domain goes from here to here. That's from -1 to 1. Those are the ratios that are okay to plug into sine inverse. And you'll notice that the domain goes from about -1.5 to +1.5, or -pi/2 to pi/2. So let me label that point. This was -1, comma, -pi/2. So that's why we have a domain of -1 to 1 and a range, the angles that we can get out of that inverse trig function, of pi/2 to pi/2. And then cosine inverse, you can go through the same type of process. The most reasonable way to restrict that would be from 0 to pi. So again, the ratios that we can plug into cosine inverse are -1 to 1 inclusive, and then the range is from 0 to pi. And then same type of thing for tangent inverse. You can plug in any number you want. Any ratio is okay to plug in, but you're only going to get angles out between negative pi halves and pi halves. So I like to think of these in terms of quadrants. So if we looked at this quadrant-wise, this is in quadrant 1 or 4. That's where you're going to get answers out. Okay. For cosine inverse, you're going to get answers between 0 and pi. That's in quadrants 1 and quadrants 2. And then from negative pi halves to pi halves, again for tangent inverse, they're quadrants 1 and quadrants 4. And again, with this one, you'll notice that that is not inclusive of the endpoints, so you can't get an angle of pi halves out of tangent inverse. The domains and ranges for the other inverse trig functions, cosecant inverse, secant inverse, and cotangent inverse, are quite a bit more complicated. I've got an example of those right here. You'll notice secant is related, or secant inverse is related to cosine inverse. You'll notice that the angles, or sorry, the ratios that we can plug in are ratios that are less than or equal to -1, greater than or equal to +1, kind of the complement of this right here to some extent. And then we have the same range as far as angles, but we can't get an angle of pi halves out of that one. Again, taking a look at the graph of secant will give you an idea as to why it works that way. But let's go ahead and do a couple of problems really quickly. And this one is a little bit deceptive. It says we want to find the sine inverse of the sine of 5 pi fourths. So this right here is an angle. What we get out of that is a ratio, and the answer that comes out should be an angle. Well, like we talked about earlier, if you're plugging something into a function and then we apply its inverse in a composite fashion there, you'd think we'd get back to the angle that we started with, but we don't, and it has to do with the restricted domain. So let me show you why it doesn't work that way, why the answer to this is not 5 pi fourths. So that's not it, and we're going to figure out why. So let's take a look here. If I draw a picture of this inside stuff, so I'm just focusing on the sine of 5 pi fourths. Okay, so this is pi halves, this is pi, 5 pi fourths would be about right here. Okay, now we want the sine of that angle, so we want the sine ratio here. So that ratio is going to be negative radical 2 over 2, and if we wanted to draw the rest of this stuff, we could. None of that matters because all that matters here is we want the sine of 5 pi fourths. So this is going to be the sine inverse of, what is the sine of 5 pi fourths? It's negative radical 2 over 2. And then we're asking ourselves, I need the sine inverse of this particular ratio. Well, let's come back up here and take a look at this. Remember, the sine inverse had a restricted domain, okay, or the original sine graph that we worked with. That left us with a range for sine inverse of negative pi halves to pi halves. So this angle that comes out has to be an angle that's between negative pi halves to pi halves inclusive, which 5 pi fourths is not. So there's no way it's 5 pi fourths. So let's take a look here. Again, keeping in mind that we're in these two quadrants, I need a sine ratio, a y coordinate on the unit circle that's negative. So that's not going to be up here because it would be positive. It would have to be down here. Okay? So I need an angle down here, negative radical 2 over 2, radical 2 over 2, that's 1. This is going to be 45 degrees, or that's the reference angle there. If we measure that from standard to position, that's going to be negative 45 degrees, or that's going to be negative pi fourths. So the answer here is negative pi fourths. There's our answer. Now, the simple way to do this problem is to just recognize that this is just in the wrong quadrant. Let's flop it over here into the quadrant that we need. This has the right sine ratio. Recognize that as negative pi fourths as far as an angle goes, and there's our answer right there. Okay? Now, let's take a look at this one, because this one is also kind of interesting. Let's find the cosine of 2 pi thirds, and then find the cosine inverse of that. Now, this is an angle. That whole thing, what comes out of that, should be a ratio. And then we're going to get a ratio for an answer, but it's got to be a ratio that's between 0 and pi. Now, if you look really closely on this one, we can just look at it and tell what the answer is, but let's talk about why that is. So let's again focus on this right here. Let's focus on the cosine of 2 pi thirds. 2 pi thirds is about right here. And let's see, we need the cosine. So 2 pi thirds, that would be 120 degrees. That would mean we'd have pi thirds, or 60 degrees here. That means this is negative 1/2. That means this is radical 3 over 2, and that's 1. Again, these two sides don't really matter much, okay? It's just that we want the ratio. The ratio that we want out of this is the cosine ratio. The cosine ratio is 1/2. So the cosine of 2 pi thirds is 1/2. So here's what we want. We want the cosine inverse of negative 1/2. We want an angle between 0 and pi that has a cosine ratio of negative 1/2. Well, if you think about all of those, it's this one right here, okay? So on this one, the answer is that angle right there. So we started with that angle, we took the cosine of it, we got a ratio from that, and then we took the cosine of that, and we got right back here. And the reason that this one is the angle that we started with is because that angle lies in the range for cosine inverse. All right? Now we've got a couple more problems to take a quick look at. And these are helpful in Calc 1 and in Calc 2. So let's take a quick look and see if we can figure these problems out. Again, we've got a composite of some trig functions and inverse trig functions. And on this one right here, again, we're just going to focus on this right here. That is a ratio. It's an inverse trig function, so this right here needs to be a ratio. So let's make it look like a ratio. Let's make it look like a fraction. So I'm going to focus on this expression, sine inverse x over 1. This is the opposite side, and this is the hypotenuse. So let's draw a picture of what this looks like. And remember, it's sine inverse, so we've got to be in this quadrant, either in quadrant 1 or 4. So if this is x and this is 1, using the Pythagorean theorem, call that b squared plus x squared equals 1 squared. So b squared equals 1 minus x squared, and b equals square root of 1 minus x squared. Now, I don't need a plus or minus on here because you remember we are in quadrant 1 or 4. This horizontal component, this x coordinate here, is always going to be positive. So this is square root of 1 minus x squared. So here's what we're dealing with. We're dealing with this picture right here, and I want the cosine ratio for this particular angle right here. Well, cosine is going to be the adjacent over the hypotenuse. So let's look at that. If my picture is radical 1 minus x squared, x and 1, and this is my angle, here's my adjacent side, there's my hypotenuse. So that's going to be 1 minus x squared over 1, which we can write very simply 1 minus x squared. Useful tool, very useful tool. Okay, so we've changed something that involved x's, cosines, sine inverse, trig functions, and stuff like that to something that's just got a radical in it and a polynomial underneath, essentially. So let's use that same idea to solve this next problem. Again, this is sine inverse, and I'm going to think of this as opposite. Think of that as hypotenuse. Same type of picture. Opposite is x, hypotenuse is 4. Using the same argument, we can figure out that this is square root of 16 minus x squared. And what I want from this is I want the tangent. So I want the tangent from this one. So if this is the angle that I'm interested in, and again, this is just a general picture because we don't know how big x is. Well, let's see, the tangent would be the opposite over the adjacent. So the tangent of that angle right there is going to be x over square root 16 minus x squared. And it doesn't seem like that expression like that would make much sense or be useful. It looks pretty ugly, but it is actually useful. And we'll get to a point where maybe even in this class we could see where that would be useful. Anyway, let's do the last problem right here. I'm going to pull up a calculator that I have because we want to evaluate secant inverse of -2. Now, some people will look at this and they'll think, well, hey, that is secant. Secant is the reciprocal of cosine, so let's just do this. Let's do 1 over cosine inverse of -2. Well, we've got a problem with that. If I do 1, oops, clear these off. Let's do 1 divided by cosine inverse of -2. Well, you should notice a problem right here. Cosine inverse only accepts ratios between -1 and 1. So if we hit enter, we're going to get a domain error. So here's what we're really after, and here's how we really do the problem. What we do is we say, look, I don't have a secant inverse on my calculator, but I do have a cosine inverse on my calculator. And since these are reciprocal trig functions, I take the reciprocal of this. So this is going to be -1/2. So let's do that right there. So I'm going to do cosine inverse of -1 divided by 2. And you could put in 0.5 if you wanted to. This is 120 degrees. So there's our answer there. But remember, we like to think of things in terms of radians. So I'm going to hit the mode. I'm going to come down here and I'm going to change that into radian mode. Go back here and recall that last command and hit enter. And I get 2.09 radians. Now let's just double check and confirm that that's right. And let's see why that would be the case. If you think about measuring 0 and pi halves and pi, let's put these in decimals. This would be about 3.14. And this would be about 3 divided by 2. So this is going to be 1.5. It's actually 1.57. So if you think about where 120 degrees is, 120 degrees is right here. But if you think about where 2.09 radians is, if this is 0 and this is 1.57 and this is 3.14, this has got to be about where 2.09 radians would be. All right? So that finishes up all the pre-calculus that we're going to review. That certainly isn't everything that you need to know, but it should cover the basics. And by doing the diagnostic worksheets, working on the stuff that I gave you from Chapter 1, you should be in pretty good shape. Please come see me if you've got a question. Send me an email or something like that. Otherwise, we're just going to start rolling with Chapter 2. It's on limits. And we'll take a quick quiz on Monday as well. So thank you very much for watching.